This is Lecture 9 in the FOA series of lectures on premises cabling. In this lecture, we're going to talk about fiber optics for premises cabling. When a lot of people think about fiber optics, they're thinking about outside plant fiber. They're thinking about large crews of people with big machines and giant spools of cable, putting cable underground or running it up on poles. But we're talking about premises fiber optics, and it's really quite a different game. Fiber optics is widely used in premises applications, whether it's in telecom closets, shown on the left, or in central offices, shown on the right. And rather than large crews of workers and lots of big, heavy equipment, premises fiber optic cabling is generally installed by one or two workers, often working in crowded telecom closets like this. But what we want to see is we want to see cabling installed in a neat and workmanlike manner, like in these two large enterprise applications. When installed, fiber is often mixed in with copper cabling, as you can see in these two pictures. And when it is, it's often run not just as a cable laid in a cable tray with other cables, but is put in interduct, which is used to protect the fiber optic cable from the heavy weight of all the copper cables around it. A fiber optic data link is actually pretty simple. It takes an electrical input, conditions a signal, and converts it to an optical signal using an LED or laser transmitter. It transmits it through a fiber optic cable plant to a receiver on the far end, where a photodiode converts it from optical to electrical, and signal conditioning transmits it out as a signal compatible with the electrical system being connected over this link. Most high-end communications equipment is available with fiber optic ports directly. But for those that only have copper ports, you can buy a media converter. And a media converter is basically nothing but a transceiver, like that fiber optic data link we were just looking at, with a transmitter and a receiver that interfaces directly to a copper port in a piece of communications equipment. You can also use them to convert multi-mode fiber to single-mode fiber. And they're typically very small and very expensive, like the little blue box you see on the equipment here. To ensure a fiber optic link will work, we look at the link power budget. The link power budget considers the output power of the transmitter and the input power required for the receiver to get a specified dB loss for power that can be lost in the link. We then analyze the optical fiber in between for the length of optical fiber and its attenuation coefficient and the loss of all connectors and splices. We sum that up, and that becomes the total loss that we expect from the cable plant that we'll be installing. And we want to ensure that that matches the dB loss budget of the transmitter and receiver that we're going to run over that cable plant. A fiber optic cable plant consists of a number of components. We have a cable, which protects the fibers in the application environment, connectors which join fiber or connect to active devices so they can be disconnected in the future for rerouting or testing, splices which join two fibers permanently, hardware that provides the mounting and protection for the connectors, splices, and cables, and test equipment, which checks the performance of the complete installed link. Here's the four most common types of fiber optic cable used in premises application. Tight buffered cable, like the zip cord at the top, is typically used for patch cords. Distribution cable is popular because it packs a lot of tight buffered fibers in a relatively small cable, which is easy to run and easy to terminate in a premises environment. Loose tube cable is sometimes used in premises environments, but it's more unusual because it's typically an outside plant cable filled with water blocking compounds. Tight buffer breakout cable is actually a whole bunch of simplex tight buffer cables inside a common jacket, which makes it easy to pull and then break out and terminate for use with patch panels or active equipment. All premises cable must carry identification and flame retardance ratings per the National Electric Code, paragraph 770 in the United States, or equivalent fire and building codes throughout the world. Cables without marking should never be installed indoors, as they will not pass inspections. Inspecting fiber optic cable is a very questionable subject. Most electrical inspectors are not aware of checking fiber optic installations for anything other than ensuring the cable is marked for flammability, although they are getting more and more involved for looking at things like installations in a neat and workmanlike manner and ensuring that all cable penetrations of firewalls are properly fire stopped. While most cables simply include a quantity of fibers of the same type, there are two other cable types that may be used in certain applications. A hybrid cable includes two fiber types, typically multi-mode and single-mode, and is popular for large enterprise backbones and on campuses, where some equipment may run on multi-mode fiber, some may run on single-mode fiber, and single-mode fibers are included for future expansion. There's also composite cable that includes fiber and copper conductors. The copper conductors can either be coax, twisted pair, or power conductors, and they are typically used in specialized cables for unique applications. Connectors can be used to create demountable terminations for fibers, like in patch panels, or to connect to transmitters and receivers. Splices are permanent terminations of two fibers and are typically done by fusion or mechanical splicing, and the splicers are then sealed in a watertight enclosure and put into some location where they may never be touched again. These are the most popular connectors used today in fiber optic systems. The ST connector has been around since the mid-1980s and was the first connector with a ceramic ferrule. The SC connector is a plastic version of a similar connector that uses a push-pull attachment as opposed to the bayonet of the SC. The LC connector was developed in the late 1990s as a small connector to allow higher density in patch panels and smaller transceivers for equipment. The MTP connector, or MPO as it's sometimes called, is a multi-fiber connector. It can have 12 or 24 fibers in the connector and is used to create prefabricated cabling systems with one interconnection interconnecting 12 or 24 fibers. Fiber optic cables can be terminated in the field using adhesive polish techniques or pre-polished splice connectors that are just attached with a splice to the fiber. You can also use prefabricated cable assemblies, such as the one shown below. Some of these assemblies use single fiber connectors, which are then sealed in a plastic boot for pulling the cable, and some use multi-fiber cables like the MTP and modules that break the cables out from the MTP connector to regular single fiber connectors. Prefabricated assemblies are simple and easy to install, but still require testing. Permanent joints between two fibers can be done with fusion splicing in an electric arc or mechanical splices in a mechanical device that holds two fibers together with index matching gel between them to reduce reflections. In actuality, splices are rare in premises fiber installations, where connectors are normally used to allow easy moves, adds, and changes. Once a fiber optic cable plant has been installed, it must be tested. Testing starts with continuity testing with a visual tracer or fault locator, which ensures that the cable is continuous and makes sure that the cable has the proper connections. It's really polarity testing, making sure that a transmitter will be connected to a receiver. Insertion loss testing uses a source and power meter, which emulates the way the cable will actually be used by a transmitter and receiver and gives a loss reading that we use for acceptance testing. OTDR testing can also be done on some premises cables if they're long enough, and it's used primarily as a troubleshooting tool. Insertion loss testing uses a source that emulates the transmitter source and a meter that works like the receiver detector. We use launch and receive cables because they allow us to mate to the cable plant under test to test the connectors on either end. This measurement gives us a loss value for the cable plant that is equivalent to what the actual transmission system will see when it's used on that cable plant. This is the test that's used for acceptance testing. If the cable plant is long enough, optical time domain reflector testing can be used to look at the cable plant, take a snapshot of it, and determine where splices and connectors have been made and if they have been made properly. However, one of the biggest problems we have here at the FOA is people calling us wondering why their OTDR tests don't tell them the same thing as insertion loss testing. Well, OTDRs don't work the same way as insertion loss testing, nor do they work the same way as the system you're testing. So it's primarily a troubleshooting tool. The other problem with OTDRs is they don't work on short cables. They require a long launch cable and cables typically more than 50 meters long in order to be able to test it all. If you don't have a long cable, the information you get from an OTDR may be totally erroneous and very confusing. Installing optical fiber cable plants is as easy as installing copper, and maybe easier, since the fiber optic cable can be pulled at a higher tension. The terminations are often easier than working with all those twisted pairs, and testing is much easier, quicker, and cheaper. Go to the FOA online reference guide for lots more information on fiber optic installation. Go to the FOA website at www.thefoa.org.